Our lesson today is on vectors, and it's somewhat long. I apologize for that. So let's go. Let's hit the ground running. A vector is any quantity with magnitude, which refers to its size, and direction. And we're going to work plenty of problems to show you what we're talking about here. And we want to talk about notation. We do have a special notation for vectors. It's similar to the notation we use for array. And I'm going to show you over here because that vector notation might be a little hard to see over there. Of course, if we're talking about ray xy, it looks like that. That's array. When we're talking about vector xy, we have the little arrow on top, but it doesn't have both sides. So just remember when you're using notation for a vector, you're going to only have half the little arrow on the top. Okay, so suppose we have our vector KW here. What do you think KW stands for? I think it stands for killer whale. Look at that great picture of that killer whale right there. So we got KW, all right? So there's our vector. The magnitude of the vector corresponds to the distance from the initial point, and so the initial point, this is just like with the ray, the initial point is the first point that you name, and the terminal point is the end of the arrow there. So that's the magnitude. The direction corresponds to the direction in which the arrow points. So this vector's direction would just be pure north. All right? So we're gonna see some in a little bit that are not that way. Not that they'll be so many degrees south of east or so forth. So we'll see that in just a minute. All right, you can also use an ordered pair to talk about a vector, but when we use an ordered pair for a vector, we don't put parentheses around the coordinates. We put these kind of little brackets here, you know, sort of like the less than and greater than symbols. So that's the notation we use for a vector. The magnitude and direction of the vector correspond to the distance and direction of the vector from the origin. So we're just going to put xy right there again. And I promise you we're going to do enough problems here in just a minute that you will understand just what I mean. So let's go ahead and look at some. Here's an example. We have OL, the vector. You see it here in red. How do we write that as an ordered pair? Well, remember, we just need the x component and the y component. And it says round to the nearest tenth. So, all right. So, what's our problem here? We don't know what the x component and y component are, but we do know the direction of the vector. It's 50 degrees here. 50 degrees we know, and really the nice thing about vectors is we're still just dealing with right triangles. So everything we've learned so far about right triangles, you know, the Pythagorean theorem, our trig that we've learned, that's all we're going to be using to find the magnitude and direction of vectors. And the good news is that vector that we're finding, it's always going to be the hypotenuse of our right triangle. So let's see, if we want to find x here, how is x related to that 50 degrees? That would be the side adjacent, right? So if we have the side adjacent, then we're going to use the cosine, of course. So the cosine of 50 is x over the hypotenuse, which is 65. And if I solve that for x, I'm going to cross multiply. I'm going to have 65 times the cosine of 50. And that's going to be approximately 41.8. So there's my x component. I'll put it up here. And we're going to use trig again for y. What do we know? Y is the side opposite, so we're going to use the sine of 50 degrees. And we know that that is y over the hypotenuse. So y is going to be 65 times the sine of 50, and that's approximately 49.8. So our vector here that we want to express, the magnitude of this, well, no, this is not the magnitude. I'm sorry. We're just expressing this as an ordered pair. We'll do magnitude here shortly. And so what do we have? Our x, we got that right there. It's 41.8. Our y value that we got is 49.8. But look here, guys. I go to the right, which is in the positive x direction. My y direction is down to get to the terminal point of that vector, so that's going to have to be a negative number. All right, so we just look in the direction that we go, and that helps us determine whether our coordinates are going to be positive or negative. Okay, here's one very similar. So I would like you to pause here and work this little problem and come back and check your answer. Okay, I did exactly the same steps that we did in the problem above, and when I got my two components, the x component 307.3, the y component 54.2, I just have to take note that traveling from the initial point, I'm going left and down, so both of those components are going to be negative. All right, now, we talked about direction just a minute ago when I was pointing that out with the killer whale vector. Here's what we do to describe the direction. You see how this angle, here's our vector in red, and the angle made between the vector and the horizontal here is 25 degrees. So I just use that angle to describe the direction of this vector by calling it 25 degrees. And what am I? I'm a little south of west, right? So I just call it 25 degrees south. I said west, but it's south of east, right? South of east. Okay, and this one over here, it's 35 degrees. And what am I here? I'm a little bit east of north. So this one is going to be 35 degrees east of north. So that's all there is to describing the direction of a vector. Let's see what we have next. Oh, how about you do this one? What is the direction of the vector below? And then the question is, do you think there's more than one way to describe the direction of this vector? All right, well, I know it's 60 degrees. The direction is 60 degrees, and what is it? It's south of west, right? South of west. So the question now is, could we describe this direction in a different way? Sure we could. We could use this angle here, right? We could use that angle, and we know what that angle is, don't we? Because we know the sum of the two angles there is 90, so this one's 30 degrees. So we could call this the direction of this vector 30 degrees west of south. Either one is accurate. Okay, so now let's find the magnitude. Let's find the magnitude. And remember, I told you magnitude is the size of the vector. And since all these problems are done using right triangles, basically we're just finding the hypotenuse of our little diagram, our little right triangle that we've set up in our diagram. So as you would imagine, we definitely have to draw a nice picture for ourselves. So here we go. Wait a minute, I want to do that with black, I think. Use my other colors for my vectors. Okay, what do we have? An airplane lands 40 kilometers west. So I'll do that blue. I'll do the airplane in blue. So 40, there's our airplane, and 25 kilometers south from where it took off. So that's 25. And I'm going to draw the vector, the airplane's vector in red. He went 40 west, 25 south. So here's our vector that represents the airplane, right? I'll call that P, since that's our airplane. Use vector notation to describe the trip. Okay, let's do that. Vector notation right here. This trip is negative 40, negative 25, right? And what are the approximate magnitude and direction of this guy's flight? Okay, as I told you, the magnitude is the size of this vector, this red vector, and as you can see, that is the hypotenuse of this little triangle here. And since we called that P, here's the notation we use for magnitude. We put our little vector inside of an absolute value symbol, and we would use the Pythagorean theorem, right, to find the length of this vector, or if it was just a plain old side of a right triangle, we'd say that equals the square root of 25 squared plus 40 squared. So that's just what we're going to do here. 25 squared plus 40 squared. And when I add those together, I get 2,225. And it doesn't tell me what to round to, but just like I did above, I'm going to round it. Well, let's see. I think I've rounded it to the nearest whole number, so I'll just do that again. All right. Usually, I know in almost all cases that we've done so far in this unit, we've wanted exact answers. In other words, simplified radicals. But when we're talking about these real life situations with vectors, we don't want to know that this plane is 5 times the square root of 89 miles from home. We need a number that we can relate to. And so when we do round this off, we end up getting about 47 kilometers. All right, so he's 47 kilometers from his point of origin. And how do we find our direction here? We need this angle right here, this green angle. What sides of the triangle do I have related to that angle? I've got the side opposite, which is 25, right? And I've got the side adjacent. So which trig function am I going to use? I'm going to use tangent, right? So I know the tangent of that angle, and we'll just call it A for lack of a better name, is the side opposite over the side adjacent. And so how do I get that angle? Remember what I got to do? I got to take the inverse tangent. Inverse tangent of 25 over 40 equals A, and that's approximately 32 degrees. So we're going to say our vector is 32 degrees south of west, right? So there's what we wanted to know. Speed and direction, magnitude, no, I'm sorry, not speed, magnitude, and in this case it's how far is he from his point of origin? How far is he from the airport? So there we go. All right, so I have one here very similar to this one. I want you to pause your video and I want you to draw your picture, set it up like I did, and see what you get for your answer. All right, here's our diagram. We know that our plane lands 246 miles east and 76 miles north from where he took off. So, of course, the vector notation, both components will be positive. We found the magnitude of the vector, in other words, the hypotenuse of that right triangle, and in this case that's corresponding to how far the plane is from his point of origination, and we did that right here as you see, and we got approximately 257.5 kilometers, and we used the inverse tangent just as we did above to find the direction of his flight, and it turns out he's about 17.2 degrees north of east. Please put a star there. If you have any trouble with this, let me know and we'll talk about it in class. All right, how do we add vectors? How do we add vectors and what's it called when we do add them? When we add them, we get what's called a resultant. And all we have to do to get a resultant vector of two vectors is add their x values together and add their y values together. Okay, so here's a little clip that I pulled out of the book to show you. If I have vector A and I have vector C and they both have x components and y components, I just simply add those together to find my resultant. So let's do a couple of examples to make that more clear. Here we go. We have A and C vectors. A is -4, 3, and C is 1, -2. What is the resultant E? All right, let's do E with green. And what do I do? Well, I just add my x values. So I got -4 plus 1, and my y values, -3 minus 2. And that gives me -3, -5, right? So my resultant, I'm just going to come over here and I'm going to go left 3, 1, 2, 3, and down 5, 1, 2, 3, 4, 5. So here's my resultant vector right there. There's E. Okay, that's all there is to it. How about this one? What is the resultant of vector 2, 3 and vector negative 4, negative 2? And it says draw a sketch. Okay, let's draw a sketch here. So we'll let this one be A, just like above. We'll let this one, well, we'll do it in red too. We'll let this one be C, and once again, we'll let our resultant be E, just to do it like we did above. So A is negative 2, I'm sorry, positive 2, positive 2, positive 3. So this looks about like A right here. Right 2, up 3. And then for C, we got to go left 4 and down 2. So C is going to look something like that. Of course, I'm estimating because I don't have real graph paper. And we want the resultant E. All right, well, let's find it mathematically first. We're going to do 2 plus negative 4, which is negative 2, and then 3 plus negative 2, which is positive 1. There's my resultant. So to sketch that in, all I have to do is go left 2 and up 1, and there's going to be my resultant vector E. Okay? So what I want to show you here, and of course because my drawing is, I don't have grids, so it's not a great drawing. But look at this, guys. When I'm adding vectors, so if I wanted to add vector C to vector A on my picture, I could have put vector C at the terminal point of vector A, right? Using the same angle, and it would have come down here, and then vector E would have just been the vector that connects the point of origin to the end of vector C. So sometimes when we're doing real life applications, we will draw it that way, and you'll see that in just a minute. And speaking of real life applications, what would be some for adding vectors? How about this? We've been talking about airplanes. How about if the airplane encounters a wind? Okay, so if the airplane has wind resistance or it has a tailwind, in any case, that's going to be two vectors added together. So airplane flying in wind. Can you think of another one or two? If you do, write them down there. Okay, so let's see. Oh, here's one. Boating. How about this? Boating, yeah. It's, very seldom are you going to be in a totally smooth current. So the current will have a vector itself. So let's see. Let's put our picture over here of our little boating trip. The speed of the powerboat in still water is 35. The river flows directly south at 8 miles per hour. If the powerboat heads directly west, all right, I'm going to draw him in here with red. My boat, he's going to head directly west, and what is his speed? It's 35. 35. Okay, so there's the powerboat vector. The river flows directly south. Okay, I'm going to do that in blue. You know how water's blue. And I'm going to put that on the end of my boat. I could have put it over on the y-axis, but I don't know. This is just one way of doing it. You could definitely do it the other way, and you'll get the same correct answer. Okay, so what does it say? What are the boat's resultant speed and direction? Okay, how are we going to find this? Well, resultant speed and direction is what we're looking for right here. This is the vector we're looking for. And let's see, what could we call this? Well, we'll just call it R. How about that? Resultant. That seems like a good enough name. Okay, so first of all, let's go ahead and, just for fun, write the vector representation for R. It's negative 35, negative 8, right? They didn't ask us to do that, but we like to do that anyway. So if we want the magnitude, remember what we're doing? We're just finding the length of that hypotenuse. So we're going to have 35 squared plus 8 squared. And when we round that off, what do we get? We get about 35.9 miles per hour. So you see that current is actually helping him to go a little faster. Of course, he's not going directly west anymore, but he is going a little faster, so maybe that's a good thing. And now we need our angle. We need our angle for our direction, and we can see that it's south of west, right? It's south of west, and just like before, we're going to use the inverse tangent of side opposite, which is 8, over side adjacent, which is 35, and that's going to give us approximately 12.9 degrees south of west. Okay? All right, we got one more problem, and this is a little trickier than this one here, so I'm going to go ahead and do it with you. If you have had enough of listening to me now and you want to try this next problem on your own, feel free to do that. Great idea, but I'm not going to pause here. I'm going to keep talking you through it. So here we go. Of course, I'm going to draw my representation first of my vectors. What do I have? This time I'm back to an airplane, and his cruising speed is 530 miles per hour. He's cruising directly east, so let me draw him in here with red. There's my plane, and 530 directly east. Okay, now I have an 80 mile per hour wind blowing 40 degrees south of west. So I'm going to put that right over here. And see, in this case, it would make it more difficult if I added this vector, if I add the wind vector onto the tail end right here of my plane vector, it just makes it a little more complicated. So I'm going to put it right over here. And what is it? It's 40 degrees south of west. Okay. So that little angle there is 40, and I do know the magnitude. I actually know how strong that wind is. It's 80. So we're going to call that the wind vector, and that's 80 miles per hour. Okay, so there's our sketch. We got our sketch. Express both vectors in vector notation. So the plane's easy. The plane vector is easy. It's 530. 0, right? Because he's not going up or down at all. He's going due east. Now, we got to get our wind vector. Let me come over here. Wind vector. What do we know? All we know is the magnitude or the speed of the wind and the direction. So we don't know our components yet. We're going to have to use trig to find those. So let me sketch them in here. I'll do that. Well, I don't want to do it with green. I'll do it with, I'll just do it with red, okay? And I'll dash it in. So there's the x component we're looking for. There's the y. So y, x, and that all this over here on the left of the origin, that is our wind vector, okay? So here we go. Let's see, we've got the hypotenuse, so we're going to have to use sine and cosine, right? So I know that the cosine of 40 degrees is going to be the side adjacent, which is x, over the hypotenuse, which is 80. So x equals 80 times the cosine of 40, which is approximately, what do I have here? 80 cosine of 40, which is about 61.3. And so there's my x component. And then I know that the sine of 40 is going to be y over the hypotenuse, which is 80. So y equals 80 sine 40, which is approximately 51.4. So there are the x and y components of my wind vector. And let's see, I'm going left and down, so both of those have to be negative. Negative 61.3, negative 51.4. Okay, so there we go. We got those. Now we need the sum. We need the sum. That's our resultant, right? I'm going to do that in green. Our resultant is going to be 530 minus 61.3, right? And that will give me about 468.7, and that's positive. And then I have 0 minus 51.4, so that'll be negative 51.4. So let me sketch that resultant vector in. I got to go right 468.7 and down 51.4. So here's my resultant, something like that. Okay? And now I need its direction. That's all that's remaining is the direction. So what do I know here? Let's see. Let me go back to black. I know there's a lot going on here. Okay, let me go back to black. I know that this y component, right, it's negative 51.4. That's 51.4. And the x component of our resultant is 468.7, right? And so how do I find the angle? Well, I got to use the inverse tangent. The inverse tangent, I'm looking for this angle right here, guys, that I'm highlighting in black right now. So I'm going to use the inverse tangent of the side opposite, which is 51.4, divided by the side adjacent, which is 468.7. That's going to give me my angle, my direction, and that is approximately 6.3 degrees. And what is that direction? Well, it's south of west, right? South of west. West. Why do I keep saying west? Right is east, not west. My apologies. Clearly, look at your resultant. Don't let me confuse you. Try as I might. Here's my resultant right here. Clearly, the angle is south of east. Okay? All right. Well, that's our lesson. Please let me know as soon as you get to class if you have any trouble with any of these. I do know it's quite a new concept and quite a lot involved. And so practice, practice, and we'll see you next time.